Okay, so the last video dealt with surface ocean circulation, and that is different distinctly than deep ocean circulation. The ocean is very, very deep, on average, maybe 5,000 meters deep, so close to 3 miles deep. But wind energy can't penetrate that deep. Energy transfer just isn't that efficient moving downward. The wind blows on the surface of the water, and then that surface water interacts with the layer of water below it, putting it into motion, and then that acts on the layer of water below it, right? And it propagates downward through the water column, but it doesn't go all the way down. A very, very strong wind might cause mixing down to 100 meters. A hurricane or something like that might mix down to 200 meters. But the ocean is 5,000 meters deep, right? And so this is just this very, very superficial layer, okay? We talked about the Ekman spiral and this idea that because of the Coriolis effect, the wind blows, but water in a net sense, the overall movement of water is not actually in the same direction as the wind. It's actually offset because of the Coriolis effect to the right in the northern hemisphere and to the left in the southern hemisphere. And so this figure here, shown at the left, is an example from the northern hemisphere, where the net movement of water is actually 90 degrees, shown by this white arrow here, 90 degrees offset to the right from the direction of the wind. The surface water doesn't even go in the same direction as the wind. It actually goes 20 to 45 degrees offset, depending upon what sort of spatial scale you're looking at. But in a net sense, overall, it's 90 degrees, okay? It's called the Ekman spiral. It's a really important concept in physical oceanography. It leads to a variety of effects. Probably most importantly, it leads to upwelling. And upwelling is really important because it represents a transfer of deep ocean water back to the surface, okay? And as we learned, deep ocean water, right, and so that happens here because the wind is blowing this direction, right, as indicated by that arrow, and Ekman transport, or the Ekman spiral, says that, well, if wind is blowing that way, water is actually moving away from the coast here. And if you're just sort of scooping water away from the coast at the surface continuously, the water has no choice but to come up from the deep and fill in, sort of backfill as you scoop water or transport water away from the coast at the surface, right? And so that drives this concept, or this idea of upwelling, drives upwelling. Upwelling being the idea that, or the term that we use to refer to that. Okay, upwelling transports deep ocean water back to the surface. Okay, that's important for a variety of reasons. But mostly it's important because deep ocean water is distinctly different than surface water in a variety of physical and chemical parameters. All right, and so it's a lot colder. All right, and that's intuitive, right? The sun shines, and just like the wind can't penetrate all the way to the ocean floor, nor can the sun. And the sun actually penetrates about the same distance, maybe 100, 200 meters, depending upon how turbid or how much particulate matter is suspended in the water. And so it heats that upper surface, and it gives rise to this temperature anomaly. The surface water is very warm with respect to the deep water. The deep water is much colder, okay? And this rapid zone of change we refer to as the thermocline. These are important terms. The thermocline refers to this temperature anomaly, all right? Warmer water is less dense than colder water, and it's quite happy to just sit up here on the surface. All right, surface water is also less salty. We call the mineral name, as we learned, for sodium chloride is halite, and so we call this rapid change, or this anomaly in salinity, the halocline. Okay, surface water is less salty than deep water, and if you dissolve more salt into water, the volume of water doesn't increase, but the mass does. And so mass divided by volume is density. That is by definition what density is. And so if you dissolve more material into water, the density increases. All right, just like with air or any substance, warmer, less dense substances like to sit up higher. Okay, and so there's this density contrast that's shown in the far right panel here. And we have this term called the pycnocline that refers to this density gradient. But in general, because of its higher temperature and lower salinity, surface water is less dense than deep water. Okay, now that drives this stratification. And stratification just refers to the fact that there's inhibited vertical mixing between the two. Surface water stays at the surface, deep water stays in the deep ocean. As we'll learn as we progress through the material this semester, biology really influences environmental chemistry. And most of the productivity and the biology occurring in the oceans is occurring in the surface ocean where there's light, right? Because there's light. But some amount of that material sinks down, and it transfers a lot of elements and compounds with it. Transfers organic carbon, but it also transfers stuff that's in that organic matter, like nitrogen and phosphorus, these really important elements, nutrient elements that we need to build our biomass in addition to carbon, right? We're carbon based, but we have tons of nitrogen, tons of phosphorus, a whole suite of other trace elements. Those are really key. And so nutrients, as a result of this, are transferred from the surface ocean to the deep ocean. It's something that we'll get into a lot in subsequent lectures. But at this point, it's relevant. And so as a result of this, the deep ocean water, or water in the deep ocean rather, is higher in nutrients than water in the surface ocean. And so upwelling, like this example here of coastal upwelling, can drive biological productivity and lead to really rich ecosystems. And so most of the important fisheries in the world are in locations where there's strong upwelling, like off of the coast of the west coast of South America, like the Chilean margin, the Peruvian margin. Those are strong upwelling zones. Similarly, on the west coast of Africa, the Namibian margin is a strong upwelling zone. Also California, we have really strong fisheries off the west coast of North America because we have strong upwelling. Okay, so surface ocean circulation is driven by the wind primarily. That can lead to upwelling, transfer of deep ocean water to the surface. But how do we get this low density surface water into the deep ocean? Well, we do that primarily through the formation of sea ice. And that's what this slide here is talking about. Sea ice forms when the surface ocean water freezes. And when water freezes, much like when it evaporates, it leaves most of the dissolved solids, salt in this case, behind. And so the residual water, the water that doesn't turn into ice, becomes saltier and saltier and saltier as that ice formation continues. As a result, its density increases and it's able to sink down deep into the deep ocean. And so we call this bottom water formation or deep water formation. There are a couple of really important sites that deep water forms. One is off the coast of Antarctica. We call it the Antarctic bottom water current. And the other one is in the North Atlantic. It's called the North Atlantic deep water current. And so the combination of surface and deep ocean circulation lead to this kind of conveyor belt-like circulation system for the global oceans. Okay. In general, the outcome of this, one of many outcomes, but the most critical one to this, wrapping up this discussion, is that warm water is carried to high latitude, transferring energy, right? Heat energy. And so we started this whole conversation talking about the imbalance in energy that we receive from the sun due to the fact that we live on a sphere. It ends up looking like this, right? The solid line is the energy coming in, and the dotted line is the energy going out. The energy coming in is largely visible light. The energy going out is largely infrared radiation or exclusively infrared radiation. It says that down at the bottom, emitted infrared radiation, right? And we have this surplus in the subtropics or at lower latitudes and a deficit at higher latitudes. And we're trying to reconcile that. The Earth is trying to reconcile that. Our class is trying to reconcile that, right? The Earth does so through the transport of material. Advection is the term that we use for transport, physical transport of material. The atmosphere is physically transporting air and water vapor from low latitudes to high latitudes, carrying heat energy with it. And the ocean is transporting warm water from low latitude to high latitude, carrying heat energy with it. And so the combined effect is that there is a northward, right, or poleward, right, to make it non-hemisphere specific, there is poleward heat transport. The total is shown here, and it's broken out by atmosphere and ocean. And about half of the global heat transport is accomplished by the atmosphere, and the other half is accomplished by the oceans. All right, but it's all about density contrast and pressure gradients causing flow, right? Both in the atmosphere and in the ocean. It's all just it's all really driven by density, and density is mostly driven by temperature. In the ocean, it also has to do with the salinity, right? And so that's how we create deep water. But that pretty much wraps up the discussion of atmospheric and oceanic circulation. And so we'll move from this into the solid Earth and talk about how plate tectonics works and how the solid Earth looks, and then we'll bridge those two into a kind of integrated view of the Earth as a system, and then we'll talk about how that regulates climate and biology and all the things that we observe on the Earth's surface in subsequent lectures.